Got it. Okay, welcome to the first meeting of the month of May for the Santa Barbara Astronomical Unit. Hopefully in a few months, if the COVID don't rise, we'll be back in Grand Hall, but right now it's looking iffy.
Why don't you introduce yourself? Tell us your name, sir.
Okay, wait, I got a lot of pop-ups here.
Uh-oh.
One of them says how to get rid of pop-ups. So I'm the president, Jerry Wilson, and since we haven't held elections in the last 2 years, I'm looking like a career here. So and with us is the vice president, Baron Ron Heron, who we will hand it over to in a minute. Our outreach coordinator, Chuck McPartland, and the merchant manager, Tricia McPartland, and museum liaison officer, Chrissy Cook, and our IT director and general brains of the technology here is Tom Totten.
Yay.
And our guest speaker tonight is Tim Brandt, who Ron will introduce shortly. And so first I'm going to ask to give us a brief rundown of near-term outreach events and star parties coming up.
Okay. We have, of course, a big day tomorrow, 10 a.m. to 10 p.m., International Astronomy Day out of Camino Real Marketplace. Setup time's 9 a.m. Chrissy got us a bunch of tables and awnings and chairs, so we've got all the infrastructure we need to go. We'll just see if any people show up. And I missed the Telescope Tuesday on Tuesday night, but apparently they've added a bunch of new lights, so we'll try to find Tom seems to have found a way we might be able to deal with that tomorrow night. And then coming up on the 12th is Hope School Science Night, they call it, but it ends before the sun sets. So we have a couple of people set up to go there and do solar and lunar because the moon will be up. And then on the 14th, second Saturday of every month, it's the museum public star party and set up at 7 o'clock and running from 8 to 10. And then on the Sunday, the 15th, the day after that, we have total lunar eclipse, and we'll be out at Camino Real Marketplace setting up around 7 o'clock or so to watch the total phases are pretty much from 8 to 10. And here's Tom's listing of those things. And then on Monday, the 16th, if anybody wants to come out with a solar scope, setup is at 9:30, 10 to 12 is solar observing for AP advanced placement physics students from Santa Barbara High School out at Westmont. So that, and then of course on the 20th, third Friday, is the Westmont Public Telescope Night. So that's our outreach for May.
Okay.
We managed to get a little over 1,100 people in April.
Oh, good job. And next, we can hear a little advertisement from our merch manager. We do have tempting and coveted merchandise that's available with our club logo on it and museum logos. Right?
You're doing great, Jerry. Go ahead.
Okay. Tote bags, coffee mugs, sweatshirts, t-shirts, all sorts of good stuff.
Don't forget bookmarks.
Yeah. Oh, the bookmarks are free.
Bookmarks are free. Here's Tom Totten, our fantastic webmaster, showing you on the website our items for sale. And we've got t-shirts and long sleeve t-shirts and different kinds of sweatshirts. We have a hooded zipper sweatshirt. We have just a hoodie sweatshirt. We have hats, we have bags, we have cups and blankets. And for now we have patches, but they are getting low. So you should get a patch. If you're a member, everything is $5 less than if you aren't a member. So contact me at merch, MGR at SBAU.org, and we can get together and you'll be clothed in branded clothing.
One of the few benefits of membership.
And Tom is modeling the sweatshirt there.
Yes.
Yeah.
Yep.
Okay, I'm going to hand it over to our vice president, who will now introduce the speaker.
Chrissy, got anything?
Oh.
I just obviously want to encourage everyone to please come out for Astronomy Day and the eclipse. And we're still really in need of some planetarium volunteers. We have one volunteer for the summer. So, we could use some more. If you're interested in giving planetarium shows, please get in touch.
Well, I don't know if you assumed me, but I'm a volunteer. Count me in.
Yes, you're the one, Chuck.
Okay.
As always.
You're it.
I'm counting on you. Don't you fail me now.
If COVID goes way down, I will too.
Oh, nice.
Okay, so it started.
No backing out. I heard you say it. It's
Okay.
recorded. It's on YouTube.
Are we on YouTube live?
Yes.
Okay, Pat says she can't get to it.
Sean Kelly says hello.
Yeah,
Figured he'd be listening, watching.
it says 3 people are waiting but can't get in.
Oh,
Okay,
not
well,
good.
Tom works on that. Baron, you have it.
Well, thank you, Mr. President. I feel like I'm going back to college under an astronomy major here because we got one of UCSB's finest who has talked to us before as a guest. Ladies and gentlemen, we lucked out when our scheduled guest speaker for tonight, Dr. Ben Darvish from Caltech, had to cancel due to illness. So we went to our June 3rd scheduled speaker as a last-ditch panicked effort, and doggone, we were successful. We got him, and he's going to talk to us tonight about a very mysterious subject. Let me give you a little background on this assistant professor with the doctorate at UCSB. Grew up near Boston, outside of Boston, attended Yale, studied blazars with astronomer Meg Urey, taught high school physics and astronomy and chemistry for 2 years at the American School in Kuwait. And he returned to the US and to graduate school back in 2008, got his PhD in 2013 under Professor Ed Turner. The man was a postdoc at the Institute for Advanced Study till 2017, when he moved here to our university. Last month, one of the up-and-coming students of astrophysics, to whom Dr. Brandt serves as kind of a mentor and has probably taken his classes, maybe knows him. They have the same last name, but they're not related. That was Mirek Brandt, gave us a great talk of science on exoplanets a month ago for our April 1st general meeting, ladies and gentlemen. This professor has written recent papers on brown dwarfs, primordial stellar mass black holes, and gamma ray bursts from dissolved globular clusters. But tonight, he delves into one of the great unsolved mysteries of astrophysics. Ladies and gentlemen, Dr. Tim Brandt of UCSB. Thank you for showing last minute. Timothy?
Thank you very much. Let me start my screen share. And there we go. That should go away momentarily. So thanks so much for having me. It's a pleasure to come. It was a great time when I came in person, and I really can't wait to come in person again. I've always had so much fun too, bringing my kids to your Public Telescope Tuesdays. That was one of the things we really missed when the pandemic started, and so I'm so happy that's going to be starting again. Chrissy, I think you gave a presentation at the planetarium a few weeks ago when I went with my kids, and I wanted to say it was excellent. So they really enjoyed it. So tonight, I'm going to tell you a bit about dark matter from my own perspective. This isn't my main field of research, but it's a really fun one and one of the more glamorous fields of astronomy, I think. It was named well. Some fields in physics could use better names, like whoever coined the term brown dwarf probably could have done better, made that sound a little bit more glamorous, but whoever coined the term dark matter did well. Dark energy was another one. They did really well in making that sound nice and sexy, and also convincing the Department of Energy that they should pay for research in that area. So I want to start by just summarizing, in a way that isn't going to do it any sort of justice, the overwhelming evidence that there is indeed something called dark matter. The oldest evidence is from the rotation curves of galaxies. If you follow the orbits of stars in a galaxy, they seem to be being pulled by more mass than you can account for if you just count up all the stars. That's an old argument. It dates back to Vera Rubin and arguably even further. But today, I'm not even sure that's the best evidence for dark matter. It's certainly strong evidence, but the evidence for dark matter these days is pretty overwhelming. That's one piece. Another piece is what's shown on the screen here, where I'll take a minute to try to explain what the different colors represent. So this is a pair of clusters of galaxies that appear to have actually collided. They're not solid objects, so by colliding, it means that stuff is kind of passing through one another. But dark matter doesn't really feel any sort of drag when it passes through another cloud of dark matter. Hot gas does feel some kind of drag. It does feel some pressure. And so here, the gravity, the matter, which we can trace by how it bends the light of distant galaxies, is in blue, and the hot gas, which we can trace by it shining in X-rays, is in pink, and they're not in the same place. So here, the statement is not just that there's too much mass then for us to account for in the stuff we can see. The statement is the mass in the stuff we can see and the mass in the stuff we can't are not in the same location. There are other very strong pieces of evidence that require a little bit more physics to delve into, but arguably the strongest piece of evidence for dark matter is if you look at radiation left over from the early universe. It actually has a structure that astronomers have modeled in astonishing detail, and they can get this exactly right by tuning just a few knobs, as long as one of those knobs is dark matter. Take away that knob, they can't fit it at all. So all of these pieces of evidence point to the existence of something like dark matter, and they point to it very, very strongly. The alternative would be that gravity doesn't work the way we think it does, that there's some modification we need to make. But gravity's passed every other test we've thrown at it, and it's hard to imagine a way of making gravity work differently, where in this picture, for example, you physically displace the source of gravity from the other matter. So if we accept that dark matter is there based on the strength of the evidence that I've briefly summarized and additional evidence that I haven't been able to, then the question becomes, what is it? I mean, obviously, other than dark matter, what does that even mean? It basically means that the matter doesn't interact in any way with light. Ordinary matter that we're used to, protons, neutrons, electrons, they do interact with light. Electrons interact with light, protons interact with light very, very readily. That's how we see everything around us. It's through electromagnetism that electrons stay bound to atoms, and so on. So something that doesn't interact with photons, with light, would be pretty different. There are some things we know of that don't interact with light that we have been able to detect, neutrinos being an example. They're very hard to see because they don't interact with light, and so our ways of accessing them are much, much more difficult. But the neutrinos that we know about, at least, cannot account for all of the dark matter. We understand the physics there, it doesn't work. So it needs to be something else. But beyond those basic rules, we have essentially no idea of what it is or what it could be. So we know that it works with gravity, and we know that it doesn't work or works negligibly with light, but that's pretty much it. The last thing I've put down is that we know it doesn't basically make atomic nuclei with protons and neutrons. We don't have certain isotopes of helium or of oxygen that have dark matter in them. It's all protons and neutrons. So other than that, the field's pretty wide open. And that means there are a lot of different things you can do to try to make some progress in figuring out more about dark matter beyond these basic facts, because that's basically all we have right now. There are a lot of different candidates that people think about, and people have had perhaps too much fun coming up with what they think are clever names for them. WIMPs being an example, weakly interacting massive particles. I'm sure someone thought that was terribly clever. Axions, I'm not sure where the name axion comes from, but it's an exotic new particle, a hypothetical particle. Nobody's actually detected it. Nobody knows if they actually exist. the neutrinos that we know about can't work, but maybe there's something else that's like a neutrino that could fit the bill, maybe. Another candidate that people have talked about, what if it's all black holes? Black holes certainly interact gravitationally. Black holes also don't interact with light other than absorbing photons that get too close. They don't scatter photons. They don't interact with electromagnetism the way protons and electrons do. So they would work as dark matter. The basic approach for all of these things is to try to discover some effect, some anomaly that you can't explain by traditional physics that we know about. And if you find such an anomaly, to try to wedge a dark matter candidate into that hole. Or you can take a dark matter candidate and look for a corresponding anomaly. Whether or not you find it would tell you whether or not that exists. The space of possible anomalies is ridiculously large. And so this is a vast playground in which you can do all kinds of stuff. So in this talk, I'll give you two examples within this playground from my own research. One of them is going to be to try to explain an anomaly that people have tried to wedge dark matter into, but without using dark matter. And another of which is going to be to hypothesize a dark matter candidate and show that an anomaly it predicts doesn't show up. And so in that way, try to rule out a sort of dark matter. Unfortunately, the field basically works this way for the time being until somebody makes a momentous discovery. And pretty much everybody hopes that momentous discovery will come soon when there's conclusive evidence for a new dark matter particle, but it hasn't come yet.
Tim,
So,
Tim,
yes.
there is a question from Sean Kelly.
How do you eliminate coupling through the strong force?
Yeah.
So we know that there aren't dark matter particles that strongly couple to protons and neutrons to get into our nuclei, because we don't see nuclei with anything other than protons and neutrons. But beyond that, I mean, dark matter could have its own strong coupling that where it just doesn't interact for some reason with protons and neutrons. That is possible. And so there are classes of dark matter molecules that are strongly interacting. Just you need to evade certain interactions with protons and neutrons. So even that it's not that strong a restriction on the space that the theorists can come up with. The only really strong one is with electromagnetism with light, because with light, that's where we get almost all of our information from the universe. And if dark matter interacted readily with photons, then it wouldn't be dark. It would be quite easy to see.
Tim,
So-
can I break
yeah.
in just one more time? I'll try to pass on comments that I see in the chat on YouTube and put them in the chat on Zoom. And then also I want to notify people that there's like a 30-second or so delay between what Tim is saying here live on Zoom versus when it gets to YouTube. So if someone asks a question on YouTube, it'll be 30 seconds. I mean, it'll be behind 30 seconds where Tim is in his discussion. So hopefully Tim will review that and get back to those, any questions or comments that someone might make on YouTube. Thanks.
Thank you. So there's a whole industry of people looking for anomalies on Earth. If dark matter does interact at some level with normal matter, then we should be able to see those interactions, however rare they may be. If it doesn't interact at all with normal matter, then that's unfortunate because we're not going to learn very much probably. So we all hope that it does, because that's all we can build our detectors out of. So here's one example. It's called LZ for Liquid Xenon. And the game here is to build a big tank of stuff and hope a dark matter particle interacts with one of your xenon atoms. Those interactions will be very rare. And so you have to put it in a place where other kinds of bumps to your xenon atoms will be very rare. So what they do is they go a mile underground in an old abandoned mine, well, a mine converted to this use, and they shield this detector. You can see maybe from this picture, there are water tanks, all kinds of shielding around these things. If you want to use steel for shielding, then steel that you make nowadays is contaminated with radioactivity because of tests from nuclear weapons from largely the 50s and 60s. So if you want steel that doesn't have that, you have to dig up old steel, for example, from old warships. It's a very hard game. After you do all of that, and this is many, many scientists, including there are UCSB scientists who work on these experiments. At the end, you get one of these beautiful plots like this, and that's all you get. What it means is that there are certain kinds of dark matter, some kind of mass, and how likely it is to interact with normal matter, and anything above this line you would have seen in your detector. It would have bumped into some of your xenon atoms. If there's a dark matter particle below that line, then those interactions are so rare that it's okay, you still wouldn't have seen them. So the whole field consists of drawing lines like that and gradually marching down and hoping against hope that at some point you will cross the reality of where the dark matter happens to be, and you'll have a detection and a Nobel Prize, and it'll be great. So that's one way of doing it. Till now, they haven't found anything. They continue to look, and I'm glad they're looking, but I'm also glad that that is not my particular career. Here's another kind of dark matter particle you can look for in the same way. The experiment you build is different, but the idea is the same. You're looking for some kind of interaction, some kind of coupling to normal matter that you can detect. And you can rule out dark matter, or you can rule out these candidates for certain configurations or for certain properties. And so it's the same thing. You get to color in regions of this parameter space, color in certain properties of dark matter that it can't have, and you hope that you'll eventually get to a part where you'll actually find it. But so far, nobody's been able to do so. There's no guarantee that the real dark matter particle lives anywhere on this plot. It might not be an axion. It might be a sort of axion-like particle that doesn't obey these kinds of properties. So hopefully one of these experiments will see something, but as yet, no. So if you don't want to be doing this in the lab and just digging a little bit deeper, hoping that this particular pit is going to be one where you strike gold, then an alternative is to look for space, where nature is doing all kinds of experiments all the time, and you can look for anomalies in space. It's not like these experiments where you can carefully control your apparatus and be pretty sure about what all of your backgrounds and systematics are going to be, which would arguably make you more confident in a discovery. So that's a drawback to looking to space. When you discover what I'm going to call an anomaly, that means it's some aspect of the universe that you don't understand, basically, or that you can't explain. So if you can't explain it with what you currently understand, then your understanding is incomplete in some way. That incompleteness might be boring in the sense that it's just a refinement of things you already know, or it might be revolutionary in that it's a sign of interactions or a contribution from dark matter. So this whole field employs a lot of theorists chasing anomalies and trying to explain the latest anomaly with their favorite dark matter particle. It also contains plenty of people looking at those anomalies and trying to understand them without dark matter. Another thing we can do at the bottom is to look for anomalies that aren't there, or try to characterize the things that would be anomalies under certain dark matter models that actually aren't visible. So if your favorite dark matter model, for example, predicts that stars should all gain in mass because they're constantly adding on dark matter, and you observe that stars don't gain in mass, then that would be evidence against this particular dark matter model. And so the two topics that I will tell you about today are going to fall into categories 2 and 3. One of them, explaining an anomaly with physics, astronomy that we more or less know. And second, or last, a prediction of an anomaly if a particular dark matter model was true, and then evidence that that anomaly isn't there. And by extension, that particular model of dark matter is disfavored. So for part one, I'll tell you a bit about gamma rays from the galactic center, which about 10 years ago, I think, was raised as one of these anomalies, a piece of reasonably good evidence for a particular sort of dark matter model. So to give you an idea of what this anomaly actually is, this is the sky in gamma rays. Gamma rays are photons. They're very, very high energy photons. And so they usually don't come from things like stars. To get these high energy gamma rays, you need a whole lot more energy than just a hot stellar surface. So here's what the sky looks like in gamma rays. That bright thing along the middle is our galaxy. So this is in galactic coordinates. This is what things looked like about 15 years ago. But then NASA launched a new satellite called Fermi. And Fermi gave us this incredibly beautiful picture of the sky in gamma rays. So just a huge advance over what we had before. And this advance made it possible to find all sorts of cool stuff. Here are a bunch of pulsars, and I'll tell you a bit about pulsars later. Pulsars are bizarre objects that are pretty good at making gamma rays, at least many of them are. And so that'll come back. So don't worry about what a pulsar is for the time being. I'll return to it in a little bit. These things are called blazars, and that's something that I worked on a bit early in my career when I was still an undergrad. These are active galaxies, supermassive black holes at the centers of other galaxies that are accreting material. And as they accrete material, not all of it makes it onto the central black hole, but some of it gets shot out in jets with huge, huge amounts of energy. All this material falling towards a black hole liberates massive amounts of energy, and some of it escapes through these jets. These jets have plenty of energy. These particles are so fast moving, so energetic that they have no trouble generating gamma rays. And that's what we're seeing here. Here are other active galactic nuclei, which just means supermassive black holes at the centers of other galaxies that are currently gobbling up material. We do have a supermassive black hole at the center of our galaxy, but it's pretty quiet at the time being. So it's a galactic nucleus, but it's not active in the sense that it's not really accreting a whole bunch of material right now, and it's not emitting massive amounts of energy like these guys are. Here are supernova remnants. The leftover material from a supernova can also accelerate particles and produce gamma rays. So when you take all of that stuff in the previous slides, all of those different sources, you still have all this stuff, all this fuzzy stuff from the galaxy. And we have models for how energetic particles travel through the galaxy, where those gamma rays might be coming from. And if you go through a whole lot of effort and try to model everything here and see what your model can't explain, here's the anomaly part. So that model can't explain this stuff on the right. So that is an excess of gamma rays at the galactic center. It's more gamma rays than the models, at least as they existed 8 years ago now, predicted. So is it dark matter? I mean, that's a question that people often ask when they are confronted or when they discover a new anomaly. Can dark matter particles produce extra gamma rays at the galactic center? And the answer is yes. Sure, dark matter can do lots of things. It's natural to have lots of dark matter at the center of a galaxy. That's where there's the most matter, period. And it's pretty easy to construct dark matter models that produce gamma rays, in fact. You can have do all galaxies have supermassive black holes in their nucleus? All big galaxies where we've been able to take a good look. So I'm not going to give that an unqualified yes, but pretty much. There are small galaxies where people are currently looking to see if they can find small or medium-sized or big black holes. There are really, really wimpy galaxies. I'll talk about some of them later in my talk. And those really, really wimpy galaxies, as far as we can tell, don't have a black hole or a big black hole. But if your picture is of a Milky Way-like galaxy, then every galaxy where we've really been able to take a good look seems to have them. So here's one example of a dark matter model. The black lines are the observations of this gamma ray excess. On the vertical axis, it's showing how many photons there are. And on the horizontal axis, it's showing the energy of these photons. And you can make a dark matter model that goes right through all the points. And if that indeed is the dark matter model, it's revolutionary. It tells you physics that you had no idea existed before. Here's another model where the units of this, or the structure of this plot is different, but you see those black points, another measure of this excess, and then you see a magenta line that goes right through all the points. That magenta line is a different dark matter model. So there are many different dark matter models that can see, or that can explain this excess, but if it's any one of them, then that's revolutionary. If our task is to discriminate between dark matter models and we have this observation, then we're already in good shape. But that is an excess above what we had been able to explain. So if we missed something, then we have to put the brakes on all of this. So the basic properties of this that dark matter then has to explain are that this is extra gamma rays, about 10% more than we predicted. So it's not a massive excess. And that's significant. It's not like we didn't predict any gamma rays and we saw a ton of them. We predicted, let's say, 10 and we saw 11, something like that. But it's a nearly spherical distribution of gamma rays at typical energies. This is physicist energies, 2 GeV. Don't worry too much about what that means, but it's roughly speaking the rest mass energy of a proton. And it goes out pretty far from the center of our galaxy, our supermassive black hole that we call Sag-A star. So we can fit it with dark matter, but it could be something else. And the spectrum of this ends up looking a lot like something called a millisecond pulsar, which is maybe less exotic than dark matter, but still pretty darn cool. So next I want to tell you a bit about pulsars, which came up earlier in the gamma ray sky. There were lots of them visible there. Pulsars are the burned out cores of relatively massive stars. They're neutron stars, spinning neutron stars. They're around 1.5 solar masses, but only 10 kilometers in radius. So it's a star squished to the size of a city, and its density is trillions of times the density of lead. It's basically a city-sized atomic nucleus. It's really wacky. They have strong rotating magnetic fields. So your MRI machine might have a magnetic field of, I think it's a few Tesla. These have magnetic fields that are as much as 1 billion times stronger than that in some cases. Incredibly strong magnetic fields. And when you have magnetic fields that whip around, because these things are rotating really fast, you generate magnetic fields, and through induction, the same sort of thing that a power station works with spinning magnets. You create electric fields and you can accelerate particles. So you can make really energetic particles and you can make plenty of high energy photons. You can make gamma rays. Here's an example of the Crab pulsar where you can actually kind of see, it's not the neutron star surface that you're seeing in the center, but you see the immediate vicinity of the neutron star. And it looks kind of wacky, kind of messy, but it's really remarkable that we're able to resolve this now. This is a picture taken in X-rays, not quite as energetic as gamma rays, but still very high energy photons. So what I'm going to call normal pulsars are what you typically get a while after there's been a supernova. They spin around their axis about every second, which is pretty fast, right? Imagine a city spinning around once every second. They get you pretty dizzy. The magnetic field can be about 10 to the 12 Gauss, which is quite high. That is 1 billion Tesla. And so if you compare that to your MRI machine, which uses superconductors, then your MRI machine looks pretty puny. So huge magnetic fields, relatively slow periods. And as they whip around and accelerate all these particles, they actually spin down. They turn some of their rotational energy, they give it to all of these particles that they're accelerating away. And so their periods get slower and slower over a typical time scale of 100,000 years, maybe 1,000,000 years, something like that. Then there are these bizarre things called millisecond pulsars. As their name implies, they spin really fast. So if you thought a normal pulsar spun fast with a period of about 1 second, these things spin around with a period of a few milliseconds. It's pretty ridiculous. It's about as fast as such a thing could spin without breaking up, almost. Their magnetic fields are lower, and they're formed mostly in binaries, mostly with other stars nearby. So what we think is that these millisecond pulsars were changed from more normal pulsars. They were spun up and had their magnetic fields buried as they took in matter from a nearby star. And the combination of this short period, very high rotation, and lower magnetic field means that they can spin this fast basically forever. Quite amazing. And if you work out how much rotational energy that is, just to put it in perspective, 10 to the 52 ergs, the exponent of 52 may or may not mean very much, but this is 10 times what the sun will radiate over its entire lifetime. It's more than the energy in a typical supernova. It's a quite remarkable amount of energy, all in rotational mechanical energy of a millisecond pulsar. And so then they very, very slowly radiate away that energy to a significant degree in gamma rays. So these are a really good source of gamma rays, and they are much, much more common in places where there are plenty of nearby stars where you can put them in a binary and where you can actually bump these binaries with nearby stars, not physical collisions, but by gravitational scatterings with these nearby stars, you can make a pulsar and its companion closer and closer to one another as they give that energy to the other stars in their vicinity. So these millisecond pulsars are much more common in dense environments like a globular cluster, one of which we see here, than they are just scattered around the sky. When they're actually accreting, when they're actually spinning up and getting material from a companion, they shine as what we call a low mass X-ray binary. So we can see them throughout this whole process. And those progenitors are also much more common in globular clusters. Here are the millisecond pulsars of 47 Tuc, all circled and given letters from, looks like A to Y. I'm not sure exactly how many millisecond pulsars you know of in 47 Tuc now, but it's at least 25, which is a pretty impressive number. So if you've gone and taken your telescope, then globular clusters are one of the main things that you would want to look at. They're just beautiful, right? This is a particularly photogenic example observed with Hubble, so it doesn't get much better than this. They're just beautiful clusters of stars. There are about 150 of these things that we know, and they can have millions of stars in them, the densest ones anyway. They're scattered around the galaxy. They're all very, very, very old. And if you were to be in the center of a globular cluster, your night sky would look 1,000,000 times richer than ours does. It should be pretty cool. I think I remember a rough calculation that the night sky on a moonless night in the center of a globular cluster would be about as bright as the night sky is here with a full moon. So we're missing out. On the other hand, all those millisecond pulsars, all that other stuff would probably come with a fair number of gamma rays. Maybe there would be other consequences that we wouldn't like so much. And globular clusters are dynamical systems where all of these stars interact with one another. So what you're seeing here is a simulation of 6,000 stars. A real globular cluster has far, far more than that. And they fly all around, And occasionally you might see one that just gets shot way, way, way off. Some of these stars are actually going to get shot off all the way outside the cluster. And here, I think this is as you're flying through the cluster. So it's not actually the cluster dissolving. But the way that these stars scatter off one another and the way that they can share energy with one another is really analogous to a situation with a water droplet, for example, where the molecules in that water droplet all bump into one another. Every once in a while, one of those water molecules can break free, evaporate, and carry some energy with it. The rest of the cluster will contract in the same way that that water droplet will cool when some of the water evaporates. The water droplet can evaporate entirely if everything goes away, as long as there's some way to deposit that or to some energy source to tap. So if that water droplet can keep getting warmed up by its surroundings, then it can evaporate away into nothingness. If a globular cluster can keep getting energy, then it can keep ejecting its stars until it has none left. And it turns out that if you have a few stars in the center of the cluster orbiting really, really tightly around one another, there's so much energy in that tight binary. By making it just a little bit tighter, by taking these binaries in the center of a globular cluster, you can use them as an energy source. And those few binaries can give you enough energy to basically unbind or evaporate the whole cluster. So they don't live forever. They can actually evaporate in much the same way that a water droplet does. It takes millions or billions of years, but the galaxy is 10 billion years old. And so the population of globular clusters that once existed is not the population that exists now. Here's a simulation done 8 years ago now that started out with something like 10,000 globular clusters in order to get the couple hundred that we see today. Most of the globular clusters in this original simulation are gone because they evaporated or they were destroyed in similar sorts of processes, or they can even have something called dynamical friction, where something massive moving through a sea of stars experiences something analogous to friction when a body moves through the air. So there are many processes that can destroy these. Now, you can destroy a globular cluster, but the millisecond pulsars in it can live basically forever. So those globular clusters, even if they existed only a long time ago, would have left millisecond pulsars that could still be around us today. And so you can ask, could that explain the excess in gamma rays? What about the millisecond pulsars from globular clusters that were there, but are not anymore? And so what we did to take a look was we took a simulation that someone else ran of globular cluster destruction just to see where the material from those globular clusters ended up. And then if you imagine that those globular clusters carried millisecond pulsars around with them and deposited those millisecond pulsars exactly where they dissolved, and those millisecond pulsars look like the millisecond pulsars that we see today in these globular clusters, then you've taken someone else's simulation of something completely different and asked, is that enough, with some plausible assumptions, to explain these extra gamma rays? And the answer is yes. So we can also draw a line right through all those points if we do nothing except take this other simulation and then assume that those globular clusters once existed and made millisecond pulsars that ended up looking like the millisecond pulsars from other globular clusters. So we didn't have to turn any knobs to make this go through all the points, which was pretty remarkable. I don't know if this is the whole story of the gamma rays from the galactic center, but it's certainly a good candidate for part of it, and makes it a little bit harder to have confidence in dark matter models. So there were a number of objections in the original paper to millisecond pulsars being the source of these extra galactic center gamma rays. And it was based on these negative arguments that dark matter was advanced. So if you can explain it without dark matter, then you don't need dark matter. And these were the arguments about why it can't be pulsars. And so I think here we've answered points 1 and 2. We've given a reason why we see them here today, even though we don't see the things that make them, the low mass X-ray binaries, because they're not being made today. They were made a long time ago and were just deposited there by the ongoing evolution and destruction of globular clusters. I won't go through the bottom 2 points because the answers to those objections are a bit more subtle and technical, but I think we were able to pretty well address point 3, point 4, kind of, sort of. But at that point, I think we're getting into the weeds a little bit. And there are also other explanations for this anomaly besides these. So it's not like we need to explain all of the galactic center gamma rays with this one approach. So there's a great question in the chat about where globular clusters come from. And it's really a mystery. Presumably, most of them form like star clusters today in one big burst, but that's not necessarily true. There are people who think that at least some globular clusters are the remnants of dwarf galaxies that the Milky Way accreted. It's possible that not all globular clusters were formed in the same way. There are some globular clusters where the abundances of chemical elements are different in different stars. There are others where the chemical abundances of certain elements are the same, but of other elements are different. There are a lot of things about the formation and evolution of globular clusters that we really don't understand. So this is a real mystery. As far as why their orbits are not correlated to the angular momentum of the disk galaxies, if they form before the disk does, the disk would form when material kind of collapses into a disk because it can get rid of its energy, but it can't get rid of its angular momentum. It can shine its energy away in light, but it can't get rid of angular momentum. And so it naturally kind of settles into a disk. And any stars that you form after you settle into a disk will follow the disk. And so our sun's an example of that. If you form something before you make a disk, then it might have very little correlation to the orbit of the disk. The details of the dynamics of globular clusters, how complete we are, and especially the formation of these globular clusters remain open questions. There are a lot of subtle things about the abundance patterns, the elements in globular clusters that I like to scratch my head about now and then that we really don't understand. And in fact, one of those is going to come up here, which is pretty cool. There is a fairly unique aspect of globular clusters where they do have some really weird abundance patterns where, in this case, many of these globular clusters, you see them in color here, have an unusually large amount of nitrogen relative to how much iron they have. We don't understand why. There are various explanations that have been put forward, but none of them are really convincing. So this is a mystery. Why do many globular cluster stars have an unusual amount of nitrogen in them? It's the same with a couple of other elements. Here, aluminum. You see some globular cluster stars with unusual amounts of aluminum in them. Why is that? And why are the stars with high nitrogen the same as the stars with high aluminum? So there's something going on there. It's probably connected either to how these clusters form. Maybe they formed in stages. Maybe the first stars were able to pollute stars that were already there. We don't know. But we do observe that something like half the stars in globular clusters show these funny abundances, and about 1% of stars in the bulge, this kind of sort of spherical distribution of stars around the center of the galaxy. They show these similar sorts of enhancements. So you might say that that suggests that maybe about 2% of the bulge is dissolved globular clusters. If 2% is dissolved globular clusters, half of those have these enhancements. That gives you about 1% of the stars with these unusual amounts of nitrogen and aluminum and a few other elements. And that is actually roughly what we need to explain those extra millisecond pulsars. And so from that perspective, you could think of the Fermi excess as possibly, I mean, I'm going to put in a few caveats here, the first direct evidence for globular cluster destruction, or direct evidence for globular cluster destruction together with this. In the second part of my talk, I'm going to stick to the dark matter theme, but from a completely different direction. So for this part, I'm going to start with a hypothesis that it's all black holes. This has been a fun hypothesis for a long time, and it has a really appealing feature because we know that black holes exist. We've observed pretty conclusive evidence of black holes, especially now with LIGO. So the detections of the neutron star merger in LIGO and the detection of black holes in LIGO, everything matches what we expect with general relativity and with black holes. It is essentially 100% certain that black holes exist. So that's great. We don't have to posit new physics. Another great thing is that if we have black holes and they're at least reasonably big, then this scenario will make testable predictions. One of those, for example, is if there are tons and tons of black holes floating around, LIGO can see them when they very occasionally merge. There are enough black holes, that should happen. And there was indeed a paper published that did LIGO detect dark matter? I'm going to argue no, but it's an intriguing possibility. There are other ways you could look for this. Black holes are an astonishingly dense collection of matter, and so as a very dense collection of matter passes in front of distant stars, it will magnify them. It will act as a lens. And that's something that we should be able to observe, the brightening and dimming of distant stars as these black hole lenses occasionally pass in front of them. If all dark matter is black holes, then those lenses should be pretty common, and we should be able to see that. If black holes are all over the place, then they would also change the behavior of the early universe. And so we can look for that evidence in radiation from the early universe, from the cosmic microwave background. And the thing that I'm going to talk about today is something called dynamical heating, where it's sort of analogous to the picture from the globular clusters earlier, where these different stars would scatter against one another gravitationally, and they would exchange energy. And some of the stars could get kicked out of the cluster. They could evaporate. That's a form of dynamical heating, as you evaporate those stars in the same way that you could evaporate water from a droplet. And so that is also a consequence if all of dark matter is in these primordial black holes. And that's what I'll discuss here. The basic idea behind dynamical heating is something from physics called equipartition, where if we have a bunch of molecules, gas in a box, for example, they're going to have, question. Is black hole explanation consistent with dark matter being offset from normal matter? Yes, it is. In order for dark matter to be offset from normal matter, it just has to feel much, much less drag as these clusters pass through one another. Normal matter is going to feel drag from gas pressure. Black holes will not. And so black holes will feel much less drag. And so yes, it's consistent with that. Any form of matter that doesn't really interact with photons is going to work from that perspective. So if you have different masses of molecules, then they're going to have different typical speeds. One way that you may have be familiar with this is you've heard somebody talking normally in a room. If they take a breath of helium, then their voice is going to sound like Donald Duck's. It's going to be very, very high pitched because the speed of those helium atoms and the speed of sound through them is very different from air. And it comes because helium atoms are light. They have a mass of 4 units, but well, oxygen molecules have a mass of 32. So the helium atoms will be traveling faster because physics tells us that they all get to have the same energy. So the less massive thing is going to have more speed for the same energy. Sean Kelly, doesn't that cool the remaining stars? It most certainly does. So this question is, if there's dynamical heating, then energy is conserved, so something had better be cooling. And yes, in the case of a globular cluster, if you're going to be heating some stars and evaporating them off, then it will cool the stars that are left. They need to be able to tap into some source of energy in order to not just cool catastrophically. And the source of energy that they can tap into is a few binaries that are very, very close to one another. If you have 2 black holes, for example, in a very tight orbit, and you make that orbit even a little bit tighter, you can release massive amounts of gravitational energy. So there's actually an astonishing amount of energy that you can tap into in a cluster from a few very tight binaries. But yes, energy is conserved. And so if you're going to be heating some things, yes, you must be cooling something else. So this argument that the more massive things are moving slower is going to be just as true for stars as it is for gas. The physical principle has nothing in particular to do with atoms or molecules. It can be applied to any kind of particle. And it doesn't matter if they're scattering off one another by electromagnetism or if they're scattering against one another by gravity. Same thing. So if you have stars that are typically 1 solar mass, and you had black holes that were more massive than that, let's say 10 solar masses, the stars should be moving faster than the black holes. And if you have a distribution of stars, the stars should be puffier than the black holes. If they're moving faster, they should be able to get away farther from the center. So you go and you look at one of these incredibly faint dwarf galaxies. This is a galaxy with a few thousand stars. The way those stars move, there's plenty of dark matter around. We can kind of map the matter, and there is way, way, way more matter than we can account for by just counting the stars. So if in our own galaxy, with these galactic rotation curves, we could get maybe half the matter by counting up the stars, here, we can't even get 1% of the matter by counting up the stars. It's almost all dark matter. So the dark matter, as far as we can tell, should be pretty extended. It seems to extend way past the stars. But that's not what we should see if dark matter is in black holes more massive than the stars. Dark matter black holes more massive than the stars should transfer their energy to the stars. They should heat the stars as the background distribution of black holes cools. So as that continues to happen, the distribution of stars will puff up as they share their energy. And so you can ask, how long would it take? The universe isn't infinitely old, so in the age of the universe, is it surprising that I see a galaxy like Segue 1, should its stars have already puffed way, way, way out beyond how big they are now? If the stars should have puffed way beyond where they are now, then that's evidence that dark matter isn't all in these black holes. So the approach in our equation that we solved for this was relatively simple as these things go. We were injecting energy from these black holes to puff up the stars, and then observing how the galaxy would grow with time, how long it takes to grow past its observed time. How quickly that energy is transferred depends upon how massive the black holes are and how fast they're moving. So it depends on the details, but pretty much if you started with a dense cluster of stars at the core of this galaxy at the dawn of the universe, which is about the best you could possibly do, and all of dark matter was in 10 solar mass black holes, then it should have puffed up the galaxy past what we see today in the 12 billion years since the universe formed. The more massive the black holes, the more it should have puffed up the galaxy past the size that we see. So this is evidence against all of dark matter being these 20, 30 solar mass black holes. The first black hole merger discovered by LIGO was exactly of this sort. They were 20 or 30 solar mass black holes that merged. And so if you think that that's all of dark matter is these sorts of things, then these dwarf galaxies put the brakes on that a bit, because this sort of dark matter is not kind to these kinds of galaxies. It's going to dynamically heat them. It's going to puff them up. It's going to puff them up too much to allow them to remain at their observed sizes. Perhaps the strongest statement of this problem comes from a little star cluster right here in the middle in an ultra faint dwarf. It's very, very hard to pick out these galaxies. You really need to find stars that are about at the same distance because they're just a few thousand stars. Most of the stars in this image are not part of this dwarf galaxy. So if you're just staring at this picture, you probably wouldn't pick out a dwarf galaxy. It takes much more complicated statistical analysis to pull it out. But this star cluster is even smaller than the dwarf galaxies. And again, as with the dwarf galaxies, it's at the center of a dwarf galaxy. There seems to be plenty of dark matter around in the same way that there is with all of the other dwarf galaxies. And the stellar speeds are slow. It is the slowest speeds and the smallest galaxies that are most constraining, because those are the most fragile. Okay, so we're looking for the most fragile systems we can possibly find. And if we find these really fragile systems, then we can put limits on what sorts of rampaging black holes could be out there smashing them up. So the size increases slowly at first in this model and then starts to grow. It grows as the square root of time past a certain point. And in this amount of time, it has blown past the size that we observe today. So this model is not allowed, because if this were true, this cluster would be much bigger today than we actually observe it. So it depends on the details on your various assumptions, but we have lots of these dwarf galaxies these days. And if you put them all together, then we can make a plot analogous to that one from the Liquid Xenon experiment earlier, where we ruled out some kinds of dark matter. We can do the same thing with astrophysics by not finding these kinds of anomalies. And there are all kinds of different experiments shown on this plot using different techniques to try to rule out some of these black hole candidates. The Macho and Eros curves here are from looking for that lensing as a black hole passes in front of a star and makes it brighten and then dim. All these other curves are limits because rampaging black holes will bust up binary stars and will dynamically heat. They'll bust up dwarf galaxies. And so the lack of that kind of destruction limits how many of these rampaging black holes there can be. So there is no space up here at the top. And that means that none of these kinds of black holes can be all of the dark matter. Up here at the top, that's all of the dark matter. Up here at the bottom, that's none of the dark matter. So you can pick any mass here and you can't get to all of the dark matter. At the higher end of this, for even higher masses, you are out of luck for these and for other reasons. At lower masses, I believe there still is a window. People argue about whether, for example, asteroid mass black holes could be all of the dark matter. I think that one is still open, but maybe there's a way to rule that out too. But my takeaway here is that it's very hard to reconcile black hole dark matter, at least of these sorts of masses, with these fragile galaxies as we observe them today. Because if dark matter were in these kinds of black holes, then those galaxies would be very fragile indeed. All right, so a little bit of perspective there. You have a few options in the dark matter game. And the things that I've told you about are two examples from the bottom. there's a whole industry of people in this field doing all of these different things. And as soon as people find something and the field comes to agreement about it, it will be revolutionary. It'll be a Nobel Prize, maybe two, I know, at least one Nobel Prize. I hope it happens, but there's no guarantee that it will, because maybe dark matter doesn't interact at all with normal matter except by gravity. That would be unfortunate, but it's certainly possible. So until then, we'll keep looking. The theorists will keep chasing anomalies. Other people will keep trying to explain them with physics that we understand. And we'll keep ruling out parameter space until we get to number one, we find an anomaly, and it gets stronger and stronger as we look more and more closely. We have a dark matter model that really, really works and makes other predictions. And then we have a party. But hopefully that comes soon. We're not there. So that's all I wanted to say. Thank you.
Very good. Baron, you're muted.
How about now?
Yeah, we can hear you now.
Okay.
So Tim,
Well,
I gave you a question.
Yes. Okay. So basically, all of the information that we get in astronomy is from light, from photons. And we can get that from stars. So we can follow the orbits of stars around the galaxy by measuring which way they're going, how fast they're moving. We can measure the motion of gas by its redshift and blue shift in these lines. And so that's a way that we can kind of map out how much mass is there by modeling these orbits in a galaxy. So that's one way of estimating how much dark matter there is, by modeling the orbits of stars and gas using Newton's law of gravity and seeing how much mass you need for that. Other ways you can get the mass of a galaxy or a cluster of galaxies is by using gravitational lensing, where I talked a little bit about how a black hole can act as a lens and magnify a distant star. A cluster of galaxies is a lot more spread out than a black hole, but it has an incredible amount of mass. And so a cluster of galaxies can be a lens too. You may be familiar with the famous Einstein crosses, where you have 4 images of a quasar around a central galaxy. The central galaxy is a massive galaxy cluster in that case that is lensing the distant quasar. And the lensing effect depends on how much mass there is. So we can measure the mass in that galaxy cluster by that sort of lensing effect. So there are different ways we can measure the mass. They pretty much all rely on light at some level, because practically all of our information about the universe comes from light. The only exceptions are the recent black holes detected from LIGO, occasional high energy particles that we get through the atmosphere that aren't light, and the occasional neutrinos. We have some neutrino observatories now that detect neutrinos from space. But with those modest exceptions, it's all light.
I got one question, sir.
Yes.
A stupid question of the week. If they're looking for these WIMPs, do they know what they're looking for? Are they looking for an invisible atom or a quark or a Higgs boson, some particle? You suppose there's a whole world of
they're looking for something that is weakly interacting. So what that means is it doesn't usually interact with protons and neutrons and electrons, but every once in a while it does by the weak nuclear force. And so they build a big experiment with a lot of atoms in it, and then they look to see if those atoms are getting bumped by something that they can't otherwise explain. And that's the effect that they're looking for. There are many different WIMP models. So if you ask a theorist, can you make a model do X? They'll probably say, why, yes, I can. So there are all kinds of different models for what the WIMP would actually represent.
Hmm. Do you have one of those LZ machines out at the university?
No. So many of these machines, if they're looking for very, very rare events, you want to be in a really clean environment. The atmosphere is messy. There's all kinds of stuff coming in from space all the time. And so you want to be somewhere cleaner than that. And so they take these big machines, and at least those kinds of experiments, they go deep underground. Neutrino experiments are also typically deep underground. There's the Super Kamiokanda Neutrino Observatory in Japan. It's deep inside a mountain in an old mine, because you're using the mountain to protect yourself from all those background things. IceCube is a neutrino observatory in Antarctica, and they're actually using the Antarctic ice sheet as their detector. They drill down into the ice just using hot water, and they sink all of these photomultiplier tubes down into the ice, and they look for faint glows as a neutrino every once in a while scatters off of an atom in the, or a molecule in the ice. So these are very, very rare events, and you need either a massive detector, or better yet, a massive detector and a very well protected environment to be able to play that game. For IceCube, another thing that they do is in order to avoid contamination by the atmosphere, they don't pay so much attention to things coming from above. They look for things coming from below, which would be neutrinos that went through the entire Earth before scattering in the Antarctic ice sheet. And the vast majority of neutrinos will travel through the entire Earth without scattering. That's how rarely they interact. They would pass through thousands of Earths without scattering.
And neutrinos are like photons, or are they no mass? Are they neutrons?
They have mass. They are not electrically charged. They do not interact with photons. They do interact weakly with the weak force, not with the strong force. So they do tick a lot of the boxes that dark matter would have to tick, but the neutrinos that we know about, we understand their physics, we understand their contribution to the early universe, and that's not the dark matter story.
Anybody else have a question or a comment? Chuck, what's your opinion?
Oh, happy camper. Good talk.
How about you, Tom?
I've asked my question.
What does macho stand for?
Massive compact halo object. Another
Oh.
one of those things where somebody thought they were being quite clever.
Yeah.
I couldn't change the acronym in their experiment, but I changed it to black hole. Strictly speaking, they don't have to be black holes, but I mean, that's what they would almost certainly have to be.
I'm sure you've seen the video taken by from UCLA over 12 years of stars orbiting a black hole at the center of our Milky Way.
Yes.
And there was also a cloud of matter that was on a collision course or a close path pass by of the black hole. And I read some article that said that it didn't get absorbed in the way that they thought it would if it was a black hole. And they were speculating that this might be an extended object instead of a confined black hole. It might be a lump of dark matter. Did you read anything like that?
I'm
sorry,
trying. So I remember there was a claim of, I think it was past or claimed to be tentative evidence for an intermediate mass black hole from some structure of gas that was doing something funny. I don't know if this is, if I'm remembering this, I'm reaching into the back of my memory. As I recall, I was not convinced by that argument. There are also some, I believe, clouds of gas that seem to be whizzing around pretty fast, and that I think those clouds of gas and their existence aren't really understood. I think that is on secure observational footing, but I'm speaking from vague memory now, and so
Okay.
I don't want to say too much.
Okay, thank you. Excellent talk.
Yeah, did good, Dr. Timothy Brandt.
Tim's here's another one I gave you in the chat there.
Another question?
Oh, I didn't hit enter yet. Let's see.
Oh,
There we go.
there we go. Okay. What if the black hole at the center of the Milky Way is actually a massive dark matter? Well, it is dark matter in the sense that it checks all those boxes, right? It interacts gravitationally. It doesn't interact any other way with matter as far as we know. So in that sense, sure, it is dark matter. So yes, the question, is not a black hole, but is instead a massive dark matter. So with this black hole in the center of our galaxy, it's extremely dense. And so if you're going to argue that it's not a black hole, then it would need to be larger than its event horizon, but not by very much. Because if it were much larger than its event horizon, it wouldn't be compatible with the orbits of all those stars that you were referencing a few minutes ago. So you have to jump through quite a lot of hoops to be able to do that. And we know black holes exist. For example, with LIGO, you would have to jump through a whole lot more hoops to try to explain the LIGO mergers without black holes in general relativity. So I don't know what kind of evidence that they could muster for that claim. I'm not aware of any strong evidence that the object in the center of our Milky Way is anything other than a black hole.
Okay, good.
So I certainly don't think it's a mass of the same sort of dark matter that makes up dark matter in the universe at large, but is not actually a black hole.
Aren't our models of dark matter mainly what they call collisionless or cold dark matter that doesn't tend to interact with itself much? And
Yes.
that would make it harder for it to clump?
Right. So you can have self-interacting dark matter where it does bounce off of itself. And you can play the same sorts of games that I alluded to earlier, where you see, okay, if it interacts with itself too much, then that'll make galaxies look different from what they do. And so that can't be. Same sorts of games. You can ask, okay, if dark matter is warm, as we call it, meaning the particles are moving around kind of fast, then that would change how galaxies form. Is that consistent with what we observe? And you use these kinds of things to constrain the properties of dark matter. All other things, fuzzy dark matter has been one that people have looked at recently. If it's so low in mass that quantum mechanical effects become important, then again, that changes how galaxies would look. And so you can set limits on that. The parameter space available to you if you're a theorist trying to make a dark matter model is almost limitless. So you can always find some corner that the experimentalists or observers haven't yet found and haven't yet explored, and you can always make a model in that corner.
Well, Dr. Tim, it seems to me that the argument for black holes looks pretty good, because I've read or heard, I wonder if you believe it, there's jillions of black holes. We just can't see them. The only one we know about is the supermassive at the center, right? Do we know of any other place in the sky where there's a black hole?
Oh, sure. They're very hard to find if they're just out on their own.
Really?
But if they have another star around them, then you can see them. And so there are black holes that are in binaries with other stars. Cygnus X1 is one example.
Oh.
Maybe the most famous example, I think, where, yeah, there is extremely strong evidence that there's an ordinary star and then a black hole around it. Most of the black holes, sure, they're nearly impossible to see. But some of them we can see, and we occasionally do see hints of lensing by occasional black holes, although definitively saying that something is a black hole is hard.
Mr. President, you have expressed in the past occasionally some reservations about the dark matter theory. What's your reasoning for that?
No, that again, you're attributing Mond to me. I'm just aware that there's been no for sure convincing evidence for any model yet of black holes. I am open to consider anything. I don't work in the field, of course, so. But I was wondering, certainly we estimate the mass of black holes, I mean dark matter in a galaxy, but if they are black holes, can you estimate the number of black holes that would be in a typical galaxy?
So you can estimate how many black holes you would have from dead stars. It's a lot, but in the grand scheme of things, it's not that many. If you think that all dark matter is in one solar mass black holes, for example, then there would be way more black holes than there would be stars. If there are so many of those black holes, then the arguments that I was discussing would apply, because then this vast bath of black holes would do all other funny business. If you just have the black holes that you get from burned out stars, then no, there aren't enough of them to matter from any of these perspectives.
Okay.
Well, good luck on your continuing research, Dr. Tim, and thank you very much on behalf of the club for subbing last minute. Looking forward to your speech next month, but from Caltech, Dr. Darvish, a good friend of one of our members, Joe Doyle, who he met at Mount Pinos. I'm not sure what Mount Pinos is. Is that a place where you go to see the stars? Anybody go there?
Yeah, it's an amateur parking lot. Or it's an amateur spot to go there. It's a parking lot up in the, what is the forest there?
So I hope Joe was,
Joe. Here, Gorman.
I got you. Well, appreciate you being there. And what do you think? Should we?
There's one last question that I'll get to in the chat, and then if anybody has any other last one.
Okay.
There was a Hubble experiment with Andromeda to look for microlensing events. I'm not familiar with its macho constraints. So the two that I showed were two older microlensing surveys that I think pretty conclusively ruled out machos up to a couple of solar masses, but I don't know whether those constraints need updating with that particular experiment.
Well, I got it.
Much of the microlensing today is actually looking for planets, where if you have a star and a planet, then the lens becomes very complicated, and it's a way that you can try to detect planets all the way across the galaxy, which is kind of cool.
Well, the universe is just like high school, machos and wimps.
There are some astronomers with questionable acronym choices sometimes.
We would like to make you an honorary member, Mr. President. You think that'd be a good idea?
Oh, yes, great idea.
All right.
Thank you.
Sure.
Thank you.
So, Tim, if we sent you a memento in the mail of this talk and your membership to the physics department at UCSB, would it get to you?
It would.
All right. Then you're going to be hearing from us.
Okay. Thank you.
And we'll have another meeting in a month, or at least the first Friday of June, which is the 3rd. And that will be Dr. Ben Darvish of Caltech. And don't forget our Monday morning podcast, now being websited or run by our esteemed president, 11 o'clock every Monday morning, also seen on YouTube. Any closing statements, Jerry?
No. Thank you again. Excellent talk.
Thank you. Thank you, Tom. Thank you, Ben. Ben will be next month. Thank you, Tim. And say hi to the young man that you're teaching or helping out going in his career.
I will.
Brandt. His name is Marek.
Yes, my student. I know him very well.
Okay, well, he gave a great talk on exoplanets a month ago, and we're going to have him back too. Good. So we're ready to open up. I got to tell you, Chrissy Cook, thank you for the Girl Scouts and Chuck and merchandise manager Pat. We will see you all tomorrow out at Camino Real, and see you again in a month. Monday morning, it'll be by your TV sets or your YouTube channels. Thanks, Tim.
Thank you.
Sign this off.